This here is the aircraft's cargo compartment, the front wall, and all of this is the FADEC computer, part of the FADEC system, right? And here are the plugs, right? For input and output, you see those sensors we looked at. We have a sensor, a transmitter up here called XPA, which gives the pedal position, and there's a sensor in the control chain called XPC. So all the inputs and outputs are received here, meaning the FADEC computer is here, and the plugs are very close to the engine, with the engine at the top, right? So here we can see all the various sensors and components that send and receive information. The Full Authority Digital Engine Control System, or FADEC, constantly receives critical data during engine operation. Well, this ensures everything runs smoothly. The input that the FADEC receives are three N1 signals, which it calls N1A, N1B, and here N1C. The difference between N1C and N1A or N1B is that here it is a control alternating. It is the power source for the FADEC. So if there is a situation of when you are starting the engine, the FADEC is powered by the aircraft's electrical system. From a certain point in the engine's operation, the one that powers both channels of the FADEC is this control alternate. So it has two functions. The N2 rotation for the FADEC, which are N2A and N2B, and as we'll see, there's also N2C here, which provides the power supply. The other transmitter that the engine has for the FADEC is back here. This one is already the N2 transmission. This is the N2C. This signal here is also a gear. It counts the magnetic pulses from the reduction gearbox gear to provide the FADEC with information about the N2 rotation. In this case, it would be the N2C. The N2A and N2B are on the other side of the gearbox, which we are going to see now. The other two N2 sensors on the engine are these two sensors on the other side of the engine. We saw the N2C over there. This one is the N2A, and this one is the N2B. During the course, we will understand what the N2A, N2B, and N2C are used for. Another vital piece of information that is also received by the operator is the data from the torque system. This specific engine features a specialized torque transmitter located right here. It actually measures the physical twisting of the internal shaft in real time. And this torque system includes a dedicated compliance box, a plate, which we will later learn much more about when we discuss what this compliance box is used for. The other information that the FADEC receives comes from the temperature sensors located between the two turbines, between the NG turbine and the NTL turbine, that is, between N1 and N2. And these probes right here, which are the T4.5 temperature sensors, receive their data and information from this specific compliance box that you can see is located right down here. The specific engines found in the Ariel 2 version of the Delta rocket simply do not feature these two specific compliance boxes due to the fact that they utilize a completely different system, which we are going to examine in much greater detail later on. This other transmitter is called the P3 transmitter. It informs the FADEC of the pressure in the compressor at station 3. So if you look right here, there is a specific pipe. It comes all the way down here underneath the assembly to pick up the P3 signal. It picks up that P3 signal down here in this section, where the pipe is. The pressure transmitter located right here continuously provides data to the FADEC system regarding the current P3 air pressure levels, so that P4 never becomes greater than P3. P3 must always remain greater than P4 in order to ensure that the engine does not experience a compressor stall. That is the role of the P3 transmitter. The other piece of information for the FADEC comes from this bleed switch. The FADEC needs to know the position of the bleed according to the N1 setting. So here inside in the bleed shaft assembly, there is a switch to indicate whether the bleed is open or closed. This is also another piece of information that goes to the FADEC computer. Now guys, another important command that goes directly to the full authority digital engine control computer is what we call the twist grip command. So here you have a panel called twist grip, see? It turned off, it turned on. This is so the pilot can set the engine to flight condition. So he turns it, and the moment he turns it, the twist grip light goes off. There, it went off. It turned on. And that's another input that goes to the FADEC computer. Schumacher here is operating the pedals. Now I'll show you in the back how it works. Alright, operating the pedal. You can keep going, Schumacher. You're coming back here. Let's see it working. Alright, the transmitter is right here. In one direction it's false when you press to the side. In the other direction it controls the XPA. The XPA is that part there, the blue one here. This blue part back here. This here is the XPA. It's being operated. One side is the engine and the other side is the control. One side is the engine, which only goes one way, alright? Thank you. Guys, this here is the XPC. It's right here, it's connected to the control chain. It's the one that sends the advanced signal to the over there to the FADEC system computer, to the DECU, Digital Electronic Control Unit. And it's a transmitter that has two channels. It's connected directly here to the control chain. Its adjustment is here. There's an adjustment. I'll show you how it's connected to the collective. So let's go. Let's take a look here. It's entering the helicopter. And then our mechanic here who's operating the collective is the anticipator's commander. Alright? Now guys, another important signal that is transmitted directly to the DECU and then over to the FADEC computer system is the signal coming from the start switch itself. Off, on. When you set it to on here, it's a signal to the digital electronic control, the DECU of the FADEC system for starting the initial start cycle of the helicopter. And here we also have a test switch to perform maintenance tests on the helicopter. I'll show you a video of how to perform this helicopter test. This panel is very similar, almost identical, however you want to call it, between the Aerial 2B1 and the Aerial 2 Delta. The Aerial 2 Bravo is not like this. This switch has 3 positions and does not have the ID counters. I'll record it later on the panel to show you. Guys, we're here at the bottom part of the helicopter, the belly. And those 2 sensors you see here, those 2 antennas are temperature sensors. One is for the FADEC and the other for the VMD. The FADEC receives information about the outside air temperature to process the fuel dosage through one of these sensors. Okay? This is yet another piece of information that goes to the FADEC system's decoder to manage the fuel dosage. The FADEC system, the computer is located in the cargo compartment, and it also receives the P0 pressure there in the cargo compartment, which is the ambient pressure. It controls the signal here, which enters through these 2 plugs, channel A and channel B, of the stepper motor, which is a dual stepper motor. This stepper motor controls a dosing needle that is inside here, inside the fuel control unit. When the needle is commanded to move one way or the other, this here is a resolver transmitter, which sends a feedback signal to the FADEC, telling it the position of the needle, whether the commanded position matches the current position. If one FADEC channel fails, the FADEC operates with the other. In this Real 2B1 engine, channel A always operates, and in case of failure, channel B takes over. But in the Ariel 2 Delta, they alternate from flight to flight. Here we have the small actuator, which is part of the GBCAL system. There is an electronic card under the pilot's panel that controls this one in case both FADEC channels fail. The system is controlled by the helical, which basically bypasses the fuel flow from the needle. And this helical here, folks, it will only operate based on the engine's rotation. And located right down here, at the very bottom of the unit, we have this specific electrical connector plug, which is used to provide a signal to the FADEC system to inform it if the helical is currently in the neutral position, so it can continue to operate in its normal functional mode. So every time you start up the helicopter, you'll see this needle perform a self-test to check if the helical is in the correct position for normal flight conditions. This is how the FADEC system works. Guys, here is the fuel inlet that comes from the tank, which is down here at the bottom, right? It comes here, passes through the shutoff, and is controlled by a lever in the cockpit by the pilot. It's only closed in case of fire. And this fuel comes in here from below into the low pressure pump, which is part of the HMU. When it goes into this low pressure pump, the fuel comes through this pipe. It is heated here in a heat exchanger with the oil system. The oil is hot, and then it returns back to the HMU. Before the fuel enters the needle for metering, it passes through a fuel filter. So this whole block, the low pressure pump, the high pressure pump, the filter block, right? The metering needle, the stepper motor, the helical, all of that is part of the HMU assembly, okay? And this control here, as I mentioned before, is managed by both channels of the FADEC. So then the fuel reaches the high pressure pump and comes with the HMU's metering unit. The metering unit has a needle here which is controlled by this stepper motor. In fact, it has two controls, two coils, one for channel A and one for channel B. The input from the ECU, from the DPU here, from the digital engine control, it arrives here and it stays there in the train's housing. I'll show the cargo compartment, I'll show where it is located. It controls the FADEC computer, the ECU, and it needs to know if the needle is in position. So it has the resolver transmitter. Here on the body, we have a small actuator, which is the manual override actuator. In case both channels fail, the manual override comes into operation. But the manual override only operates in response to a drop in N2, which is the N2 mechanically connected to the helicopter's rotor. Here we have a plug, which indicates the neutral position of the manual override. The computer needs to know if the manual override is in the neutral position during normal operation. And this signal, which has an internal switch, is also sent to the ECU system, to the FADEC system. Here we have channel A, channel B, and here we have the club of the manual override. There is a test for this manual override. It's in the flight manual, and I'll show you a video on how to perform the manual override test. Here is the dosing needle section. Here is the dual stepper motor, the input for both channels, and the feedback resolver. All of this, folks, is to provide the input. And how does the computer there, the Deco Digital Engine control? Now we're going to start up the helicopter locally, and we'll hear the sound of the FADEC system performing its self-test. Let's listen. The sound, right? And the usual sound. And the Yogi light must not stay on in the cockpit. It just completed a self-test. If the Gov light didn't come on, the system is operating normally. Guys, this is the VMD operation screen. We have an upper screen and a lower screen. Internally, the VMD has 3 cards, 3 modules, 1 display module, 1 module which is LAN 1 for the upper screen, and 1 module which is LAN 2 for the lower screen. This screen is also referred to as the aircraft operation screen, and this one here is for the engine. That's not really accurate because actually down here we have the aircraft information, and up here we have both the aircraft and engine operation. What indications are there on the VMD? We have a bleed indication. When this flag is displayed, the bleed is open. And analog and digital fuel quantity indication. Outside air temperature. And this field here is used to display messages to the pilot. For example, the FADEC light that turned on. For example, this light here, the Gov light turned on. When this red Gov light comes on for the pilot, it means he is operating in manual mode. Or if the yellow light comes on, it means it is in degraded mode. We will study this. What does the pilot do? He has to press this select switch here and see which hexadecimal code appears here. In this case, it's showing 00 because there is no failure. It's with this code that we can troubleshoot what is missing. To clear it, just press it again. I have an indication of T4, engine temperature, torque indication, digital NG indication, and delta NG indication in the air. On the lower screen, I will have the oil temperature indication, oil pressure indication, the voltage indication of the PP12 bus, how many volts there are, and here the indication of how much the generator is consuming, the load on the PP12 bus. On the left side, there's the fuel flow, the aircraft's hourly consumption, and the total fuel time, meaning the flight time available with the fuel in the tank. And here is also the field used for messages. With these off 1 and off 2, I can turn off the VMD channels, both channels. I cannot turn them off and on during flight, it is prohibited. When I turn it back on, I have the scroll and reset switches, which are for maintenance use, as we've already seen being used. I use this select to navigate in the maintenance section. The plus and minus are to access the previous pages. Enter is used when I select some data and I want to confirm it, so I press enter. And here bright plus and bright minus are to increase and decrease the brightness of the VMD. Guys, here we will have access to the FADEC information from the FADEC system, so we can read them here on the VMD. So I just started up the helicopter, the VMD turned on, then I turn off channel 1 and channel 2 of the VMD, right? We're behind the sensors, so what do? I hold down the reset scroll switch and turn on both channels. When it says release key, I let go. And then I have the maintenance status, the maintenance menu. What do I want to access? I want to access this FADEC data. And for that, I'm going to use the select button. So I go to FADEC data and press enter. And there you have all the data from the FADEC system. We have the NG for takeoff power, the NG for maximum continuous power, the NG limit, T4 information, the actual engine temperature, the temperature between the two turbines, the IAS speed indication, which is not used, pedal position, and this here is the XPL in percentage. I'm going to move the pedal here, you'll see. So I'm moving the right pedal, see? There's a percentage indication. Now I'm going to move the left pedal. It's dead. The left pedal is dead because this XPA sensor is connected to the tail rotor control chain, which is to slightly increase the rotor's power under certain conditions. We also have the XPC reading, the XPC from the PID column. Here it's at 10 degrees. This one here is actually the anticipator, where it's at 10.2. It's the anticipator. I'm going to show the video working, but I'll control the collective here. I'll unlock it and operate the collective, and you'll see it being controlled there. There's also a percentage reading of the collective's position here. And then I'll lock the collective again. I also have information from P3. We have the PT transmitter at engine station 3. I have an indication of the fuel flow that's being consumed. I have an indication of T0, the temperature at station 0. Actually, here it's the ambient temperature and ambient pressure. These two pieces of data are taken directly by the DECU Digital Electronic Control Unit from the FADEC system, which is in the cargo compartment. So this data and this one it takes directly. And here are the TATOs in hexadecimal, which we use for some maintenance troubleshooting. Here we have some messages, which I'll explain to you later during the course. And here we have what I call Boolean algebra, which is used to run some tests and to know whether something is open or closed, depending on whether it's a 1 or a 0, IO or I0, okay? And then to exit from here, I simply press exit. I press here, reset, so I press reset and I exit. We're starting up the helicopter, right? And right when we turn it on, It's doing a self-test. This light blinks a little, see? Doing the check. It's doing the check there, that noise we heard earlier. The light went out, there's no fault. And then we press the test button, right? We have two GOV lights, the yellow GOV light and the red GOV light. These two lights here, when they come on for the pilot, they mean something. So we have 3 levels of failure, right? The first level here is when this golden light starts blinking, which we call a redundancy failure, right? Basically the degradation is 0 and the light keeps blinking. However, when the pilot sets the throttle lever to the flight condition, that is twist grip, the light goes out, but that doesn't mean the failure is gone. Then there's another malfunction where the yellow light comes on, right? There is a degradation in the engine, but it keeps working. And when the GOV light comes on, it means both channels have stopped working. And then all the fuel management is being handled by the IBCAL. And the IBCAL is an electronic card located down here. This pedestal here is at the bottom part. And it simply controls the fuel flow to the nitrogen too. So the pilot needs to be more careful when moving the collective up and down. Well, here is one more important piece of information for you. Whenever the VMD system is currently in the maintenance page access mode, it is completely normal for this specific GOV indicator light right here to keep blinking continuously. Alright everyone, I'll show you that if I reset the VMD to normal, that GOV light will stop blinking. I turn off both VMD channels and then turn them back on. The very moment I turn it on, it should stop blinking. And look at that, it has finally stopped. So now the VMD has returned to its normal condition and operation. Alright everyone, this is the pedestal, the panel, the control panel that the pilots refer to. This is the side, on the left side. By removing this panel here, you get access to the box where the IBCAL card is located. So the IBCAL here receives a signal from N2 when both FADEC channels fail, and it simply controls IBCAL driver 12 by passing the HMU needle,